Hello friends, I am Ashutosh Kumar from 01. Today we'll progress on our tutorial of theory of computation and we'll see regular language and their closer properties. Okay. Now before going to the properties of regular language, let us do a problem. Let us draw a DFA. Okay. So I'm writing a language L, X belonging to 0, 1 star such that 0, 1, 1, 0 is a substring of okay. We did a similar problem and our problem was that x belonging to 0, 1 star and 0, 1 is a substring of x. In the previous video section we draw a DFA. Now in this we want to draw a DFA such that 0, 1, 1, 0 is a substring of x. So when we say for example 1, 1, 0, 0, 1, 1, 0, 1, so see here we are having 0, 1, 1, 0 as a substring, so this will be accepted. Okay, so we have to draw a machine M. Recall that the automata, deterministic finite automata, that was Q, sigma and delta, Q initial final. Okay, so we have to draw a model, we have to draw a deterministic model, and I told you why we are calling this type of model as deterministic. Now also I told you the what is the difference between DFA and NFA, only the elementary idea. We will study NFA in the later sections of video, but yes, we were studying DFA, so we need to know why we are calling such an arrangement DFA. So you are clear with that? Now see how intuitively, see whenever we draw a DFA, you have to think intuitively. Suppose for example, consider this as example, you are going to scan this string, okay? You are going to scan this string. So what is your state of mind? See, in every section we will be drawing some DFA, okay, so that we practice and get used to drawing it, okay? Now see, we haven't scanned anything, so what is our initial state? That we haven't scanned anything, so this is the initial state. Let us say this state as Q0, okay? This is our initial state. Now what our target is, that our target is to reach to search this 0, 1, 1, 0. So what is my favorable output? After this, what is my favorable input? That you get a 0, you scan a 0, okay? Suppose if I get a 0, then I will say yes, I am close to my goal. Now I need to scan only a 1, 1 and 0. I got a 0, good. So I got a 0, so my state of mind will be like this, that you have got a 0. Look, you have got a 0, now you have to get 1, 1 and 0, and that's all, you are done. Very good. Now suppose after this one I get a 1. Very good. I get a 1, then you will say, look, I have got 0, 1. Now I am only 2 characters away. So again your state of mind will be at, okay, so I got a 1, so I will draw again. My state of mind will be like this, that I've got a 0, 1. Now I am nearer to my goal, I need to scan a 1 and 0 only. So again you scan a 1, similarly you go to Q3 and again you scan a 0, you go to Q4. So clearly it will be a final state. Why? Because I have got 0, 1, 1 and 0 and I reached to a final state. But what about other inputs? See, when I am talking about state Q0, it is only specified about what will happen if I get a 0. So we are not specifying anything. What will happen if we get a 1? So see what you will think intuitively. If you get a 1, you will think, no, I haven't scanned even a single character that is belonging to my substring 0, 1, 1. So you'll say, okay, I must remain here. Okay, I have not even seen a favorable character that would lead us to our goal. So we say that yes, our state of mind is not changing, I am at here Q0 only. Well and good, so we have 1 and 0 for this Q0. Now we want to decide what will happen if a 0 comes here at Q1. So look what happens. I've got a 0. Suppose I got a 0 and then I got a 1. So it is good. We were changing our state of mind from Q1 to Q2. Now what if I get a 0 again? Then you say, look, I should have got a 1, but I have got a 0. So again you will hope that I should get a 1 after this 0. So you'll say, okay, I have got a 0, I will remain here only, isn't it? Why? Because getting a 0 was not our goal. Getting a 1 after a 0 was our goal, and again I get a 0. So in the hope that the next character scanned will be 1, I will remain here only. Very good. Now what will happen if I get a 0 here at Q2? See, if I get a 0 here at Q2, then I always have to go back to this Q1. Why? Because see, I've received a single 0. So receiving a single 0 leaves you at a state Q1, isn't it? That we have received only 1 0 in the hope of getting this next 1 1 and 0. So when I get a Q2, a 0 at Q2 here, everything what we have scanned doesn't matter, that is spoiled. So again we'll go to Q1, and from this state we'll again hope for getting 1 1 0. So this is good. I reached at Q1, from Q2 to Q1. Now what will happen if I now for Q2 we talk about 1 0. Now at Q3 we have talked only about 0. We didn't specify what will happen if we get a 1. See guys, if I get a 1 here at Q3, what will happen? I have scanned 0 1 1, and if I'm getting a 0, it is very good, thank you. But what if I get a 1? If I get a 1, we didn't reach to our goal, and getting a 1 leaves you nowhere. When you get a 1, it isn't like that. After getting a 1, what is the output, what is the character that you should look for after getting a 1? Obviously a 0. You have to look for a character like 0. Then and which 0? See, this was the 0 that we will look. So from where we will get it? So again I say getting a 1, I'll get to this point, isn't it? I have got a 1. Now I have to scan, I have to wait for all these 4 characters, isn't it? So again I go to, suppose the string is like 0 1 0 0 0 1 1 0. So at this juncture, see, I have got a 0, I have got a 0, I am here. I have got a 1, I am here. But then I have got a 0 again, so I will go here only, isn't it? So this way I went here, and again I will get a 1, so I will get at Q2, again I will get a 1, I will get to Q3, and again I will scan 0. So this way, now what will happen? Now when we reach at Q4, okay, when I am at Q4, I will say that yes, I have got 0 1 1 and 0 as a substring, that is why I have reached to Q4. So whatever be the string, either 0 or 1 that will be scanning, it will make no difference, because we have got the substring 0 1 1 0 in our target string which we were scanning. So this is a DFA, isn't it? Okay, if you are feeling uncomfortable in this, you can just try, practice yourself so that you get used to it. Now let us check some of the sample strings, that whether that string will be accepted by this DFA or not. Okay, so guys, this was our model, this was our machine that we draw. Now let us check what will happen if I have a string like 0 0 1 1 0 1 1. Let me make it 0 here and 0 here and 0 here and 1. Okay, see, this is the string that we want to check, and we'll check whether it is accepted by this or not. So simple. See what we can do. Let me write the string here for clarity. I wrote 0, and then I wrote 0 1 0 0 1 1 0 and 1. So these are the symbols that will scan, and we will decide which state we move on. So initially we haven't scanned anything, so I am at my initial state Q0. Okay, now we have scanned a symbol 0. So what will happen? Where will be our transition from Q0. So from Q0 scanning a 0 leads us to Q1. So I am at Q1. Very good. Similarly, what will happen at Q1 when we scan 0? So at Q1 when we scan 0, see, look, at Q1 we have scanned a 0, I remain in Q1. Again, what will happen if we scan a 1 at Q1? We scan a 1 at Q1, I will go to Q2. I will go to Q2. What will happen if I scan 0 at Q2? I scanned a 0 at Q2, so I will go to Q1. Now what will happen if I scan 0 at Q2? I scan a 0 at Q2, so what will happen if I scan a 0 at Q1? So I scan a 0 at Q1, I will remain at Q1 only. Okay. What will happen if I scan a 1 at Q1? If I scan a 1 at Q1, I will go to Q2. What will happen if I scan a 1 at Q2? I will go to Q3. What will happen if I scan a 0 at Q3? I will go to Q4. And what will happen if I scan 1 at Q4? Is nothing will happen. I will remain at the same state Q4. So see, I have scanned all the symbols, isn't it? And see, finally we reach from Q0 to Q4. Now, one important observation that you can, see from this arrangement is that, see, count how many symbols we have scanned. We have scanned 1, 2, 3, 4, 5, 6, 7, 8, and 9. Now, we have 9 symbols, and how many state I have written? The set of, call it as a string. When I call this string as a string, then I can count that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have written 10 states, obviously, which some of them are same. But the point that I want to make is that when we have scanned k symbols, obviously we will have k plus 1 states. And when I say that we'll have k plus 1 states, I do not mean that all the states will be distinct. There is repetition, obviously, that see, this Q1 is repeated and Q2 is repeated. Just keep this point in mind, that whenever you are scanning k symbols, you are getting k plus 1 states, and we'll make use of this concept in pumping lemma. In the later section, we'll see how this is captured in a lemma, pumping lemma, and we'll also see the use of pigeonhole principle. Okay, do not get confused about this pumping lemma and pigeonhole principle. When I say this, I will explain you in the next video, but for now, just remember this arrangement, that when we have k symbols scanned, we will have k plus 1 states, and using this concept and using the pigeonhole principle, we'll see a theorem, pumping lemma, which will be used to prove that some of the languages are not regular. Okay, now this was all about DFA. Now you can draw a DFA, and in later sections of video we'll have a dedicated video section where we will practice all those DFA. We'll draw DFA, and we will also see how can we minimize. Okay, so that's all about that will be in the later sections. Now when I talk about this language, we know that this language is regular. Okay, this language is regular. Why? Because we could draw a DFA. Now let us see some of the closer properties of regular languages. Okay friends, so I am writing some of the properties, that is, if L is regular, L complement is also regular. Again, if L is L1 union L2, or L is L1 intersection L2, then L is regular if L1 and L2 are regular. Okay, see these 2 points, that if L is regular, the complement of this language L, that is L complemented, is also regular, and if L1 and L2 are regular, then the union of these two languages or the intersection of these two languages will be regular. Now we need to prove these statements. Okay, so we will be proving this one by one. Now let us prove the first one. See, what is L? L is obviously any language is a subset of sigma star. We are very much fine with that, because any language, will have a combination of the symbols defined over sigma, and let us say sigma is 0 1. In the case of our example, it can be any symbol or more than 2 symbols, anything. Now when I say complement L, so this is basically X belonging to sigma star such that X does not belongs to L, isn't it? So what is set? See, when I say A is a set and A complement, let us talk about the sets. So we have a universal set like this. Let us say this is the universal set and this is A. So what will be the A complement? These things, everything leaving this. So A complement will be the universal set minus A. So in our case, what is our universal set? Our universal set is sigma star. So we can write L complement is sigma star minus L, or some people write it like this, sigma star L. So both means same. So now my question is, how can we say that when L is regular, complement of L is regular? And when I say that complement of L is regular, what we mean? Whenever we say that a language is regular, we mean that we can have a DFA for that language. So yes, now remember the previous example, that was L, X belonging to sigma star, where 0 1 1 0 is a substring of X. Okay, so and when I talk about L complement, then what will be the set of this? Every X belonging to 0 1 star such that X does not belong to L. So we will target at those strings which do not have 0 1 1 0 as a substring. So let us see how can we draw DFA for L complement. Now we'll talk about this particular example. Let us redraw the DFA of this L. Okay, I am drawing it. Okay. See guys, so this was our L. This is the machine that we draw for this L. Now I want to draw a DFA for L complement. So it's simple, We will make all these states final. These states. I am making Q0 final, Q1 final, Q2 final, and Q3 final, and this will be a non-final state. And simply we have done it. So whenever we'll get 0 1 1 0 as a substring, it will always reach to this Q4 state and whatever the character it scans after this substring, it will remain here only, and thus we'll conclude that this will be rejected. So every string which having 0 1 1 0 as a substring will reach at Q4 and this will be rejected, and obviously this was our target. And now any string which do not have 0, 1, 1, 0 will be either at Q0 or either at Q1 or either at Q2 or either at Q3, and we have named Q0, Q1, Q2, Q3 as a final state. So this is very simple, and you can just conclude that L complement is a regular language. Now let us prove how this or this one is going to be regular. Okay, so we want to prove that if L1 and L2 are regular, L is regular. So we know that L1 and L2 is regular. L1 and L2 is regular. So L1 and L2 will have DFA. Say M1 and M2 such that L1 is accepted by M1 and L2 is accepted by M2. Now write those 5 tuples. So for M1, I am writing it as Q1 sigma delta 1 Q01 and F1, and for M2 I am writing as Q2 sigma delta 2 Q02 and F2. So these are the two machines that will exist for L1 and L2. Since L1 and L2 are regular, I am trying to make a machine M for L such that it is accepted by L is accepted by M. So I write it Q sigma delta Q0 and F. Okay, and I write Q is equal to Q1 cross Q2. See, what I am trying to do is that I have two machines M1 and M2 for L1 and L2. I am trying to make a machine M for L such that L is accepted by M. So what my target is, suppose we have a string. Okay, this is a string. Now this string takes this M1 to, suppose, starting from initial Q01 to say P, and this string takes M2 starting from Q02 to say, for example, Q. So I am making the initial state of this machine Q01 as Q0 as a set Q01 and Q02. So when I draw the states of this machine, we mean that this state is a set of state. It will contain, the initial state will contain this one and also this one. Now suppose it took it to P and Q, this is strings, and now let us say that this P and Q are final states. So our final state will be P or Q, isn't it? Our final states will be P or Q. So if I write this transition function delta hat from Q, suppose this string was X, and if I write X here, so what will be our transition? So this is actually our Q01 and Q02, and I can write delta hat Q01X and Q02X, and finally I will get the states as P and Q. So I reach at P and Q, our final state. So anywhere, if a string reaches either at P or either at Q, see, in this case, suppose this is a string X and it makes you reach to the final state P, and suppose this same string X do not make you reach at Q, then also this machine will accept this X. Why? Because we are clubbing this, P and Q, our final states, the set of final state is P or Q, isn't it? So when we say, suppose the final state I am naming as Fm, then this is a set of state as P and Q, isn't it? So either we reach P or either we reach Q, we are reaching a final state in this case. So we can draw, and hence we have proved that if L1 and L2 are regular, that means we have a DFA for L1 and DFA for L2, so we can draw a DFA for L by clubbing. We are clubbing those sets and saying that this clubbed set is for this machine M. Similarly, we can do for L equal to L1 intersection L2, but in this case our final state will be P intersection Q. That means if a string X takes you from Q01 to P, then that string must also take Q02 from Q02 to Q, such that our final state is a set of P and Q, and you have to reach both P and Q, isn't it? So the big difference is this final state condition, that in this case we will define our final state as either P or Q, or in the case of intersection we will define our final state as P and Q, isn't it? And this way we can prove, and this is the intuition. In the L complement form, what we did, we just try to draw a DFA. We try to show that yes, we can have a DFA, and thus we concluded that complement L is regular. And in this case also we were trying to show that yes, we can draw a DFA for this L if there exists a DFA for L1 and L2, and similar is the case with this. Okay, so you can prove it formally. You can write down the statements and just imply these certain conditions and just prove this formally. Okay guys, so this was all for today. We'll continue in the next section. Thank you for watching. Please like and subscribe our channel.